Okay, everyone, we are on page 51, so taking notes, following along. Beers-Lambert law. There's two main things I want you to be able to do, learning goals, okay? So first one, you need to be able to do these calculations. And these calculations surround this equation that we're going to describe here in just a moment. And then the second thing that you need to be able to do is you need to be able to describe what happens to concentrations, or like if a concentration is high or low, lower than expected, you could give a situation that would result in that. So describe inconsistent results. Okay, describe inconsistent results, and this would usually be that the absorbance is either too high or too low. Higher than expected or lower than expected. We have to be able to describe why. So here's what we have going on. We can take samples of solutions that have different items in them, and we can put these solutions inside of these cuvettes. Okay, like cube, right? Like not a pipette, not a test tube. Okay. And the cool thing about this is we got the rigid sides and then we got the smooth sides. And the rigid sides are meant to be handled, like that's what we're touching and we're holding. But on the clear sides, we don't want to touch or manipulate those. We often clean those because that's where we're going to send a beam of light through. Like if I place this inside of our spectrophotometers, that's what they're called, and I send a beam of colored light, I want that colored light to go through the clear, not get absorbed by the clear and pass through. Okay? And then imagine this is going to be full with some solution that has some color to it. Now, how much of that light will be absorbed? Because we will send a certain color of light. And if this was perfectly clear, we'd get the exact same intensity of light on the other side. None of it would have been absorbed. But if the intensity of the beam is lower than when it entered, then some of those photons got absorbed by the solution. And so that's what we call absorbance. Okay? Absorbance is interesting because it's unitless. Okay, so unitless. But the reason why it's unitless is because it's a ratio. So it's this ratio of the light that's going in to the light that's coming out. And whenever we have a ratio like this, the units end up canceling, right? It's like we're dividing them, and so then the units cancel, and that's why this is a unitless quantity. So the amount of absorbance is equal to the molar absorptivity, okay? Molar absorptivity. And the molar absorptivity is constant for a solution. Meaning that I could have a solution of iron, let's say I have some kind of like 2 molar like iron solution, and as long as it's an iron solution, then that's going to be my molar absorptivity. Okay? Like the concentration can change, but as long as it's an iron 2 solution, the molar absorptivity stays the same, even if the concentration ends up being like we dilute it and now it's half as much as it was before. B is path length. For what length is the beam of light actually traveling through the sample? Okay, so back to this, it would be this distance, the distance of the cuvette, and these cuvettes are often, almost always, 1 centimeter. Okay, and see, like, the distance that's traveling, not including the walls of the container, is 1 centimeter, and so that's very intentional. If on the AP Chem test it doesn't tell you the path length, this is so common that you can assume that the path length is 1 centimeter. And then we know what concentration is. We know concentration is measured in molarity. And this molarity is the same as the amount of moles per liter of solution. Moles per liter. Great. Now, when working with this, it's important that you know the different units and that you know how to rearrange this equation. Like, absorbance unitless is equal to molar absorptivity, B is path length, and C is concentration. And here we got these interesting units for molar absorptivity. Well, let's talk about where those came from. What if I am solving for molar absorptivity and I divide by path length and concentration? So A, which is unitless, divided by B, which is path length in centimeters, and concentration in capital M, molarity, that equals molar absorptivity. So we're taking some unitless thing and we're dividing it by units of centimeters and dividing it by units of molarity. And so it's per centimeter per molarity. Or another way of saying this would be centimeters raised to the -1, molarity raised to the -1. Units are going to be important on this. I've seen questions where it says, like, what's the molar absorptivity with appropriate units? And so you've got to be aware of that. Okay? Alrighty, so I have a really cool lab that we're going to be doing with this, but I'm actually going to save it until after the test because it's a kind of lab that will take up the class period. So we're going to be doing practice problems with these instead to best prepare you for that test. Okay. Now, let's talk about color really quick. For these spectrophotometers, they send colored light, photons, with specific wavelengths, specific colors. And the reason for this is because if we have a clear solution, then the colored light will just go right through it. But if we have a certain color of solution, then that means it's absorbing and not absorbing certain light. Like, if we have, like, let's just say hypothetically that this solution is blue. Whatever it is, it's a blue solution. Okay? Maybe it's a copper solution. And we need to figure out, well, what light should we send at this blue solution so that we get optimum absorbance? And whenever something is a certain color, it's not because it absorbs that color, it's because it doesn't absorb that color. It reflects that color. So what is optimally absorbed is the exact opposite from it on the color wheel. So, like, if this solution is blue, we actually want to send orange light at it. So if the solution is blue, then the best light to send is orange. Orange. Okay. Orange light. Because that's what's going to be absorbed, right? Opposite from the color wheel. So again, if we have a paper and it's green, okay, great. That doesn't mean it's absorbing green. It means it's absorbing everything but green. And what it is absorbing the most readily is red because that's opposite of the color wheel. Oh, the item is green, so what it absorbs the best is red light. Okay? So here we see absorbance, and we see absorbance happening at two different things. We got an acid and we got a base. So the most absorbance is happening for the acid at 320, that's the number that's down there, nanometers. Okay, so that would be oh, it doesn't quite have it, but it's going to be like down here, right? It's like that violet range. And so then to go opposite from that, then it means that the color is actually yellow. Like it's absorbing this, but its actual color, the acid must be kind of a yellowish color. Now, what about the base? Oh, we also get a yellowish color because we got the 400. It's absorbing 400, and so we also get kind of a yellow color. And I've seen this before where they provide something like this, but then they say, hey, this is what it was absorbed. This is the wavelength that was absorbed. What is the color of the solution? Okay, so actually let's stay back here for a second. What could happen if the concentration, sorry, not the concentration, what could happen if the absorbance was higher than expected? Okay, absorbance. Now, let's use the equation to help us with this, because we can think about it for a second. We know the equation is absorbance is equal to EBC, molar absorptivity, path length, and concentration. Okay, so molar absorptivity isn't going to change for a solution. Path length isn't going to change. Okay, but concentration could change. So if we have higher than expected absorbance, one possible reason for this is that the concentration is actually higher than we realize, like higher concentration than expected. Maybe we mixed it wrong, maybe we ran our numbers wrong, but the concentration may be higher than you expect it to be. Okay? Another really common reason for having a higher absorbance is that there's actually like smudges or like fingerprints on the clear side, on the like non-ridged side. So fingerprints would absolutely contribute to that. Because if you think about it, if I put my fingerprints on here, that is leaving something that can be that will absorb the light. That would create a higher absorbance than you would expect if the fingerprints weren't there. So that's a really common reason why we get higher than expected absorbance. Okay? So I would say those are the two most common reasons for higher than expected absorbance. Now let's talk about lower than expected absorbance. Now this is going to be due to mostly, like I'm trying to think of where this one doesn't correlate. I can't come up with one right now. It's because it has lower concentration than expected. Okay, so this could be a couple of things, like maybe we miscalculated, maybe we mixed it wrong, maybe, and this is the most common, is we accidentally diluted it. And here's how they do this when it's like leftover water. So when you use these cuvettes, you rinse out the solution, like we take the solution, we pour it out, and then we rinse it with distilled water, okay? So we rinse this distilled water, and then we're supposed to add the new solution in there. So we add the new solution in there, and then we're supposed to dump it out. And then we're supposed to add the new solution again. And the reason why we dump it out once is because what if water gets stuck on the edges? And if water gets stuck on the edges and then I add the new solution, it's actually diluting what we're putting in there. And AP loves questions like that, where the concentration is lower than you expect. And the reason why is because we rinsed it with water, and then some of the water was still in there, and then we added the solution, and then we didn't pour that out and add the solution a second time. So the leftover water in there actually diluted what we put into it, and that led to a lower than expected concentration. The last one I'm thinking of would be actually separate from concentration, and it's when we have non-optimal color of light. Like if we send blue light at a blue solution, it's not going to absorb any of that, and so that would make the absorbance less than what we would expect, right? So if we unintentionally send the wrong light at it, then that also would reduce its ability to absorb. Okay. So we are going to do one problem here together in the notes. Then we're going to do one in class and get lots of practice in. So I'm going to start here, and it's to do with this iron solution. And it says that the absorbance, so I'm just going to put my list of knowns and unknowns up here. Absorbance of the solution, let's see, the absorbance of a 5 times by 10 to the negative 5 molar. Oh, so the concentration is 5 times by 10 to the negative 5th molar solution is measured to be 0.55, and this makes sense because absorbance is unitless and concentration has units of molarity. And then it goes on to tell us that the path length is 1 centimeter. And for part A, we're supposed to calculate the molar absorptivity. Okay, part A, calculate the molar absorptivity. And our Beers-Lambert law says that absorbance is equal to molar absorptivity, path length, and concentration. And I'm solving for molar absorptivity. So I'm going to take absorbance divided by path length times by concentration. Great. Let's plug this in our calculator. Being careful to add parentheses, so whatever's on the top of the fraction stays on the top of the fraction. Find it optimal. Okay, so 0.55 divided by, in the new parentheses, path length 1 centimeter times by concentration. Okay, so without sig figs I get 11000. Now this is a 2 sig fig number though. That's 3 sig figs, that's 3 sig figs. So this is a 2 sig fig number because these trailing zeros are not significant because I didn't put a decimal. So I could leave it just like that. But my units are unitless divided by centimeters divided by concentration. So that's where we get the centimeters raised to the -1 and the molarity raised to the -1. Now part B says determine the concentration of such a solution whose absorbance is 0.36. So we go, okay, great. I knew what the concentration was and I was able to figure out my molar absorptivity. But now that I know molar absorptivity, I can figure out the concentration of an unknown solution. So molar absorptivity stays the same because it's the same solution. Path length stays the same because it's just that cuvette. But the absorbance is no longer 0.55, now it's 0.36. And I am solving for concentration. So do my work over here. A equals EBC. I'm solving for concentration, so A divided by EB equals C, or molar absorptivity, and path length, 0.36 for my new absorbance, divided by molar absorptivity times by path length. Great. Now, this was 2 sig figs. This is 2 sig figs, so I'm going to go with 2 sig figs. 3.3, and I could add all those zeros in before, or I could change it to scientific notation, times by 10 raised to the -5th again. Yep, molarity, concentration, molarity. Okay, great. All right, everyone, we have an awesome shorter video today, and so I really need you to go in and make sure that you've watched all of the Unit 3 videos so far, because remember, when we get our homework done, and the homework has been the videos and filling out our notes, we get the homework done, that's what earns us the ability to do corrections or retakes on these tests. So make sure you get into Edpuzzle and double check that you've watched all of the Unit 3 videos. If you have any questions or concerns, do not hesitate to reach out, and then I'll see you all during class.